All right, so what we did last time, we started talking about some tree-related work on the medium problem, and it was sort of quick. I just wanted to give you the very efficient algorithm of Goldman, which was published back in '72. That was the tree trimming algorithm. And let's just talk a little bit further about tree properties for medium problem, and then we'll start talking about center problem in general networks. Okay, so when you look at a tree network, there's one property. Well, it's connected, meaning that you can go from any vertex to any other vertex using a sequence of arcs. But it does not have any cycles. You never come back to yourself. So with those properties, tree networks seem to be quite special. And one particular property that strikes you is whenever you remove the interior points of a particular edge, the tree is split into two disconnected parts. And that's why you can actually analyze whatever you're doing with the minisum objective function in terms of the total weight on one side and the total weight on the other side. Now, the Hakimi proof for the general network actually utilized that, but in that one, there was no splitting of the network into two parts. Of course, it could happen if you have a bridge type of arc, which means that you might have one part and another part, and there may be only one connecting arc between the two parts. Nevertheless, that's a very special situation. In general, in a cyclic network, you are not going to necessarily have a bridge. Okay? So, however, in a tree network, the removal of the interior of any edge leaves you with two disjoint subtrees. Okay? These are called subtrees. So that's what I'm going to focus on. Let's just put some well, let's not put some weights on it, but let's just go ahead and do the following. Let y be a point of the tree network on n vertices. And now y can be an interior point or can be a vertex point. What I'm going to do is I'm going to look at disjoint subtrees when you delete y from the tree. So we're going to look at the subtrees that would result from the deletion of y from the point set y, from the point set t. We're viewing t as an embedded tree network. Okay, it's a point set. So when you remove this, if y is an interior point of some edge, then t minus y consists of exactly two subtrees. Okay? As an example, if I happen to pick y to be this particular point here, when you delete that, you're going to have a hole here. It's just deleted. And you've got one subtree here and another subtree here. Okay. So this sub-edge would be a half open edge. It would be closed on the vertex side. It would be open on the y side because y is deleted. So if this is, for example, VP and that's VQ, then we're talking about the edge VP to y, except y is not included. That's this sub-edge here. Okay? The other one is similar. There's another sub-edge here, which is, let's write it this way, y with dq. And then you've got the rest of the tree. Now, so let's focus on this situation first, where y is an interior point. Here, let me again call this the side Q, and let's call this the side P. Okay, I think last time I called them I sub P and I sub Q. It doesn't really matter. Let's just call them Q and P, where Q is a subtree union with Y and union with P. Let's put P here. So P union Y union Q is the tree itself. So my P and Q are subtrees. And they are disjoint. So here's the question. If W of P, or for that matter, W of S refers to sum of the weights for vertices restricted to any subset S of the tree. So this is true. So let WS equal this for any subset S of T. Assume now the total weight on Q is strictly greater than the total weight on P. This is equivalent to saying that if you add WQ to both sides, what do you get? You would get 2WQ here. You would get WP plus WQ here, but WP plus WQ would be the total weight, which means that WQ is greater than, so this is equivalent to saying that WQ being greater than half the total weight of the entire tree. My notation for this was capital W before, but with the new definition, this is the situation. Okay? So what can we say if this is the situation for the optimum of the absolute medium problem on this tree? Can it be in P? No. Can it be in Q? It has to be. It has to be. Can it be at Y? Y is an interior point right now.
Y might be one of, no, it's strict no.
Y
No.
isn't even in the network.
But it's in the original network. This is just partition. It doesn't. You're just using it to partition.
If it is strict, that
Okay, Y cannot be. Yeah, if it's strict, it cannot be.
Beyond the Y, but there is actually one more solution with the same.
No, no, no. That's what I'm asking. Can an optimum be on top of Y? That's the question. And if the inequality is strict like this, the answer is no. It cannot be at Y either. Okay? It has to be truly inside of Q, excluding Y. Well, Y is already excluded anyways in Q, okay? Then an optimum of the minimization of f of x, x and t, where f of x by definition is wi times dx vi summation over all vertices of the tree, that an optimum cannot exist in P union Y. It has to be in the other part. So, the same thing said in a different way, all optima must be in the other set in Q. Anybody who can prove this quickly? Or what's the idea for the proof? Yes.
Be more close to BQ, that the summation increases with
Strict slope.
distance times BQ, but it increases with distance times BP. Since BQ is greater than BP, then the summation increases. So
Okay.
they have to through BQ. So what cannot exist in Y or
Okay. Let's assume we have a, let's go by contradiction, okay? I know what you're saying, but the statement is really sort of the negation of what we want to prove. We want to prove that no point in P union Y can qualify as an optimum. That's what we want to prove. So, you pick an arbitrary point U in P union Y, and then you should show that this guy cannot be optimal. This is what we need to show. That f of u cannot be less or equal f of x for every x in the tree. So, it suffices to find a particular x here which reverses the inequality. If you can find a particular x where the inequality is actually strict, it's reversed, f of u is greater than f of that x, then you're done, okay? Then that means u cannot be optimal. Find me such an x. Yes. Now I just write, observe that f of vp is greater than f of u, but you need to really work it out. So how do you work it out, John? How do you show this? This is immediate, but how do you actually, sorry, q. Sorry, that's q, yes. F of vq is greater than f of u. It's greater. Pardon. You're right, smaller. Yeah. f of VQ is smaller than f of U. Since U is somewhere here, could be also inside the subedge in this left side, and I've got VQ here. Since f of U is by definition equal to how much? Distance Wi times dx du vi over all indices. And if you partition this into two parts, you're going to have Wi du vi for vi in P, and then you're going to have the other part, Wi du vi for vi in Q. Okay. So how do I proceed from this point on?
Moving the point from U to VQ.
From where?
U to VQ.
U to VQ.
Yeah. You will increase your cost by a smaller weight times that distance.
Okay,
and
but
decrease it with a larger weight with the same distance. That's why you cannot be optimal.
what do you know about U, VQ, and VI? When VI is in the Q side, you know that VQ has to be some point along the path connecting U to VI, because all paths from P to Q necessarily pass through this edge. They have to visit that, okay? That's where you use the tree property, actually. And you have to make it explicit. Otherwise, anything else that's said in a blurrious way will not make it work. So you need to utilize this particular fact. So what we do in this case is for vertices here, we're not really doing much. But then for vertices here on Q, we observe that we're actually multiplying Wi by the distance from U to VQ, right? Plus the distance from Q to I. Okay. Where would that take me to now? So how do I make use of this? Or should I do something else?
Summation is times EQI is constant.
Go slowly. Summation. Let me write it. Okay. Summation.
Weights times DQI.
DQI.
It's same. It's constant.
Well, what is this summation on? Okay.
They are changing.
So you're multiplying this term with that and separating that out. And then you've got this. Is that what you're telling me? Plus Wi du vq so this is what NS is suggesting, right? Plus we have the other stuff, which is Wi du vi. Now this part here is not dependent on the index I, so I can certainly take that like this outside of the summation, and that would give me, let me write that one first, du vq times w of q. The summation that remains gives you the total weight on q. Plus, you've got this one. And you've got that one. So how do I move from here to where I want to? I want to end up with this. You see, that's what I want to end up with. That's what we're trying to show. Can you replace this as? Do you want to replace Hydra? Well, I'm not sure. FVU. F of u. Well, this is not F of u. Because this is only a summation on P.
We can du this du minus
du vq minus
vi dqi.
dqi. Is that correct?
No.
du vq or vq?
Du vq minus dqp.
Or qp. Okay, so what you're saying is the distance from u to, well, in this case, vi is somewhere here, okay? Going from u to vi, do I have to visit here? Not necessary. Yeah. So, what do I do? You tell me. No, that would be too long. There are shorter ways of seeing these things. I want you to, where? Slowly. Which one are you replacing?
I'm assuming that u is equal to eq.
Here. You cannot assume things in a proof.
I am going to write this equation in that case. I'm going to compare these two cases.
I'm not following what you're saying because u is already picked. I cannot change it. U is an arbitrary point in P and Y side. I can't change it. We have to go by rules. We can't change that. We cannot make any assumptions on that.
My aim is to see the difference between this case and the case where the point I select is U. I'm going to see if this is very
You're forcing me outside of the proof. The proof is going in a certain way. You cannot change the rules of the game as you go along. Now, if you want to start a new proof, that's fine. I can admit that, okay? But as we go along with what we have already started out with, we cannot change. And that seems to be what you're suggesting. So that's why I'm resisting to that. Okay? Maybe I don't understand what you are trying to say, but yeah, you need to word it differently then. Yes?
You can write FVQ and subtract it from this. Some of the sums will actually eliminate each other, and if we end up with something positive, decidedly positive, then the inequality will be strict.
Okay, that's a possibility.
I think the middle part is not the same. Summation of VR.
Well,
is above VQ.
okay, guys, just try to think. Just try to think. All you're trying to do is that. I mean, it's really not this difficult. But you seem to be getting into different stuff. Yes?
I claim that this value is always greater than or equal to the second term of this equation. That is just
Coming short, yes. Now that I can go with that. That this is greater or equal something.
this. I claim that this is greater than equal to plus V1. I claim that this is like
Okay, why? That's something you need to show, because this is precisely f of VQ, right?
Yes.
But how do you get there? That's the important part.
Okay. Since U is here
Uh-huh.
and Y is here
Okay.
and VQ is here, the distance from U to VI, U is here,
Is less than.
for example. This distance is less than this distance.
Less than or equal
Less than or equal to this
something.
distance.
What is that? Use the triangle inequality. What are you using? I mean, just use it, but don't say a lot of things, but just say the correct thing. No, do it here. Do it here. Yes.
DUVI
Is less or equal
is less than or equal to
distance from U to
distance from U to
VQ plus, yes, distance from U to VQ plus
VI to
VQ to VI.
or
Is this any good?
Not this way, not. If we put U to VQ on the left,
It won't help.
distance U VQ, distance VI VQ has to be on the left side. Distance VI VQ is smaller than or equal to distance U VQ plus distance U VI.
We have.
We could move
Yeah,
from the
we cannot use that because we've got this excess. If we did not have this, we somehow want to change that. So we want to end up with f of VQ. This is what you want to end up with. This is proof by saying, but proof by saying is not acceptable. So you need to show this algebraically. John, if you have a suggestion, come and do it.
Maybe we can like if we change this with VP, and then we can.
What do you mean change?
I mean to get the lesson.
You mean you want to go back to the earlier part of the proof and do something else? Is that what you want to do?
No, I do it for me. Like,
Oh, if you replace it,
yeah,
don't say change then. If you replace it
with this,
then of course this will be strictly greater.
Then I can.
I see what you're saying. Okay.
Reopen this, and I can get distance U times VQ plus distance U VI summation for WI VI.
Do it clean. I know what you're doing, but just don't do it on the little bit like. Just do it clean, okay? Yeah. Okay. You've got something there. Yeah. I see what you're saying.
First of all, I place this with
Uh-huh.
summation. Plus this
Okay.
summation I will call
He's just replacing W of Q with W of P, which is something smaller. Okay.
doesn't change this. Let's call I and VI of P VI.
What is I there? Is that the same as that?
This one.
You just named it I. Okay.
I just named I.
Okay.
I could distribute this sum of weights and reopen this.
Do it. Just do it. Just do it.
This is equal to summation VI sum distance UVQ.
Okay.
Summation of, let's put summation of I here, WI, then also at this part, distance UVI plus I, then this part from triangular inequality is less or equal to summation.
Wait, just a second. Wait, don't go too fast. What did you do here?
I distribute the weight.
Don't use the word distributed. Just tell me what you did.
VP is summation of VI's that corresponds to the.
Okay,
versus
then
VP.
that would give only this much.
Yes.
But what is this? That's what I'm asking.
This is this part.
So you are combining the two. Okay.
Yes,
Okay, I see.
This
Okay.
length is
I
from
see.
triangular inequality. This is
Okay.
smaller than or equal to distance VQ VI.
Okay. Good. Uh-huh.
Then we have here summation of VI DQI.
That's the I part. Okay.
Yes, this is the I part. Then this whole term.
This is F of VQ.
Yes, this is F of VQ.
Okay. He's right. Okay. He's right except for a small point. Thank you. He's got the right idea. So what he did is, at this point, he just put this in here. Okay. He called it I. And this is a strict inequality because of the assumption between the relationship of P to Q. And this one is simply the summation Wi du VQ. We've got the same summation here in the same set. Okay. So he's taking and combining the two summations. And the distance, the sum of two distances here, when you replace it with the distance between VQ and VI, that would be less or equal, okay? And so this would be a greater or equal, and the entire thing would give you F of VQ. So with strict inequality, that would simply tell you F of U is greater than F of VQ. This is correct. Okay, yes.
You don't actually need the I part. You simply open up the FVQ and subtract it.
Where are you? Because I'm not following what you're saying.
I'm at the inequality.
Here or here?
No, above that. Yeah. Above that. Yes. That's the opened up version of FU. And if we write down the opened up expanded version of FV cubed and subtract it, we end up with something positive. I've actually solved it here.
Okay, so you have an alternate?
Yes.
Come and do it. Could be. It's the same thing said in a different way.
Same thing, but
The same thing in different clothing, probably, huh? Okay.
yes, probably.
Just do it on the side here. Just you can continue from here.
The opened up version of FV cubed.
No, continue with either equality or greater or equal or whatever. Oh, you're going to add and subtract the same thing?
Not add and subtract, just simply subtract. Can we erase this?
Yes.
So this is
I can't simply subtract something
this is
because I have an equality here. If you're going to
F of u. So we have F of u, and we claim that F of u is greater than, strictly greater than FV cubed. If I expand this, this becomes plus. This becomes that.
Okay.
And if I subtract this from this expression, which is V F of u, and if I end up with something decidedly positive, then I prove this strict inequality. I move it here, and I end up with something positive.
Again, you're not saying it right. You may have a right idea, but you're not saying it correctly. I can't subtract something here. Because I'm talking about very simple, something very simple. F of u is equal to that. Now, if I subtract something from here, all I can say is this is greater than that minus that something. I can say that. Otherwise, I cannot continue. You see what I'm saying?
No, I mean, if we have this, this is also true.
Well, I did not start with that. Then you have to start with, I'm going to look at the difference between f of u and f of vq. If you start with that, and finally, if you show that this is greater than 0,
yes.
Fine. But I did not start with that.
Okay.
You see what I'm saying?
Okay.
I don't want to change the rules along the way. Okay, but if you begin with this,
I do this without the additional i's and transformations to WP and such.
so what you're saying is, let me do this. Maybe I see what you're saying. Maybe this is what you have. Let me begin with that, actually, which means that I subtract f of vq here, which means that I also subtract f of vq here. Let's just retain the inequalities, which means I also subtract that, right?
Yes.
And finally, when you get here, you've already got your minus f of vq. And you've got minus f of vq, but now you write it in open form. So you're subtracting this. Is that what you're saying?
Yes, and these two actually eliminate each other because they're the same thing.
Okay, let's see.
EQI.
Okay, so that goes with that,
And
okay?
if we combine this, we end up with with something like this. And from triangular inequality, this has to be less than the VI VQ. And this actually becomes WP.
Okay,
And
okay.
this is the same as that one.
So they cancel.
Sorry, this is actually this. And this is the same one. So we actually have WQ times something minus WP times the same thing.
Okay.
And this is strictly greater.
And
this
now
is
you-
positive, this is
okay.
positive, everything is positive, so we end up summing strictly positive,
Okay.
and the strict inequality is proved.
Okay, yeah. That would all be okay if you begin with this, okay? That's fine. All right, so at any rate, even though these things sometimes look intuitively quite straightforward, just working out a proof may be a little bit difficult. And I just wanted you to sort of have a taste of that. And probably at home, if you start thinking about this, you can probably come up with a more straightforward proof. But you wouldn't start with that. If you start with that, then this is eventually where you get to. Okay? All right, let's take a 10-minute break. Actually, let's make it a 5-minute break, and then we'll continue. Okay?